Well, hello and welcome. In this video, I'll be covering section 4.5, which is over rational functions. My goal for you by the end of the video is to be able to, for a rational function, find the domain and graph the function, identifying all asymptotes, as well as being able to solve applied problems involving rational functions. So we'll go ahead and start with defining what a rational function is. Essentially, a rational function is a ratio of two polynomials, hence the name rational, with the key part of that word being ratio. So anytime you have a polynomial being divided by a polynomial, that is what's going to create a rational function. Important to note that whatever the polynomial is in the denominator, in this case we're representing it with q of x, cannot be the zero polynomial. In other words, I cannot have any sort of division by zero. And when it comes to identifying the domain of said rational function, essentially it will just be all values that, or we would get rid of all values that would actually make that q function equal zero, which is something that we've practiced multiple times throughout this year. So anytime you see one of these rational functions and you have a question that deals with domain, we would just want to factor the denominator and set it equal to zero, and then eliminate those numbers from the list of all real numbers. Now, graphically with these types of functions, we get a lot of different things and a lot more intense things that start happening. So these are just 6 random examples of some possible rational functions that just hopefully kind of provide you with a little visual. Notice with every single one of these, it looks like there's somewhat of a vertical line that causes a little break in the graph. So notice that they do not connect on the left side and right side, and some of them, like the bottom one in the middle or the top one on the right, notice it actually breaks into multiple parts where it actually has 2 breaks or even more when it comes down to it. So what we're going to be doing in this section is trying to find a way to analyze a graph well enough that we could at least draw a rough sketch such as these examples here. And so that's going to be kind of the main emphasis from here until the end of the video. So again, just to reiterate, I said this earlier, but just to make sure that we're all on the same page, the domain of these rational functions, essentially we just get rid of anything that makes the denominator equal 0. So any sort of restriction, usually you can represent with like an x cannot equal symbol. So if you wanted to be a little bit more succinct with your domain, you could say something like x cannot equal and then list out your numbers and separate them with commas. Or you could also do the interval notation idea of doing like negative infinity until you get to a number and then picking up on the other side of that same number and just continuing on in that same fashion until you eventually get to positive infinity. So for example, this would be one way or one template that would get rid of 2 different numbers. So let's say, as an example, if I were to set the denominator equal to 0 and I'd get 2 solutions of like -2 and +4, in this case I could rewrite that either in this x cannot equal format, or I could go ahead and just put -2 as the last number of this first one, but then the first one of the next, go until 4, and then have the last one pick up where 4 left off. So notice it kind of where one parenthesis stops, the next parenthesis needs to begin, but I do need to use parentheses to represent the fact that that number is not included with the interval. I'm just getting as close to it as possible, such as like -2.000001 would be super close to -2, but technically still not equal to it. So again, just the ability to rewrite these in 2 different formats. I personally prefer the x cannot equal with rational functions, but if you like the interval notation, notice you still have the ability to write it out. It's just a little bit more, I guess, time and effort to be able to do those. So as far as some examples of how we can actually find the domain, we've got all of these examples, which actually I believe are the same as the graphs from earlier. But as far as how would I write these, well, essentially it would just be take whatever I see in the denominator. So if I look at all of the denominators, it's going to be set each of these equal to 0, and I don't really need to focus any attention on the numerator at all. So when it comes to the first one, if I just set x equal to 0 unsolved, notice I really don't get anything other than x equals 0. So as far as how could I write the domain, well, I could say x cannot equal 0, or in interval notation, I could say from -infinity until I get to 0, skip that number, and then pick up on the other side of 0 and go on till infinity. So either of those 2 would be acceptable. In this case, the table's asking for interval notation, but really, honestly, when it comes down to the questions that we'll be asking of you, we just want you to, in some way, shape, or form, be able to identify what that domain is. If I look at the second one, I'd have x squared equaling 0, so I would technically have to square root. And there's no such thing as a plus or minus 0, so notice this one also still would have the exact same domain of x just cannot equal 0, because that would make division by 0. Or again, I could write it as negative infinity until 0, and then from 0 to infinity. The third one here, it looks like I might need to factor that one. So if I think in terms of what multiplies to the negative 2 at the end, that would add to a positive 1. That should be a positive 2 and a negative 1. If I set that equal to 0, I get two solutions this time of x equaling negative 2 and positive 1. So again, I could just write this in shorthand of x just cannot equal that negative 2 and positive 1 that we just identified, or in interval notation, negative infinity until negative 2, since that would come first on the number line, from negative 2 until 1, and then everything after 1. So it takes a little longer to write the interval notation, but as stated, it is something still we can do. If I move on to the next one, I'm going to do it off to the right here. I would just set 2x minus 6 equal to 0. So this one would require a couple of steps. I'd have to add 6. So if I added 6, that would turn into 2x equals positive 6. And then divide by 2, that would leave me with x equaling 3. So for this one, I would just say, well, if x equals 3 makes the bottom 0, I just need to make sure I cannot equal 3. Or go from negative infinity until 3, skip it, and pick up on the other side of 3. Next one, notice it's very similar to the third example. I should just factor it. This time I need to multiply to negative 2, but add to negative 1. So this time it would essentially just be x minus 2 and x plus 1. So my two solutions for that would be positive 2 and negative 1. So I could say x just cannot equal those two numbers, 2 and negative 1. Or from left to right on the number line, negative infinity until negative 1. Then from negative 1 to 2. And then from 2 to infinity. Very last one, relatively straightforward. Just set x plus 1 equal to 0. Subtract 1 from both sides, I get x equals negative 1. So for this one, I would just have x could not equal negative 1, or negative infinity until negative 1. Leave it off with a parenthesis, and pick up on the other side of negative 1. So again, the process with these, sometimes you do have to do an extra step of trying to factor it just to make it easier to set equal to 0, but the general concept of setting them all equal to 0 and then just getting rid of those numbers is something we've been doing since the beginning of the year, so hopefully this is not too big of a stretch with these rational functions now coming at you on a lot more, I guess, higher frequency than maybe they had been in the past. But our approach still remains the same. Set the bottom equal to 0, get rid of those numbers, or write it in interval notation where I have parentheses next to those numbers. So now we'll go ahead and talk about graphically what that means when I have some form of restriction on my domain. So with these types of functions, if there ever is a restriction on the domain, in other words, something that makes the denominator equal to 0, one possible way we could graphically deal with that is a thing called a vertical asymptote. So again, vertical asymptotes are essentially going to be kind of dotted lines that are vertical that I get close to, so usually it means it's either going to have to spike up near it, or potentially it might need to spike down near it, but it never actually physically crosses it. And so by identifying those, that would allow us to draw these dotted lines such that I know, okay, it's going to be getting close and going either super vertical or by either pointing straight up or almost straight down. But notice again the formatting of these, since they are vertical imaginary lines, it's going to have the format of just x equals a, so long as a is a number that makes a 0 in the denominator, as long as there's no common factors. So that's going to be something we talk about later. If there are common factors, it creates a second type of thing, which is actually just like a random hole in the middle of the graph, where actually it would come in one side and then back out the other side. So this would be an example of what a hole would look like graphically, whereas the first thing I did, that was more of what would a vertical asymptote look like. So when it comes to determining vertical asymptotes, first thing I would do is factor both the top and bottom. Look to see if they have any common factors. If they do, I would go ahead and cross them out. So very similar to how we approached the solving of the rational equations earlier in the year. So if there's a common factor or a common parenthesis on top and bottom, we can go ahead and cross it out. And then any of the factors that are left in the denominator, that's what I would set equal to 0 and solve for. So anytime that happens, if I end up getting some value, in this case we'll just call it a, that makes the denominator equal 0, then the vertical line x equals a is what we would call a vertical asymptote for that graph. And we'll go ahead and work through a few examples of how this works in the next slide. So as mentioned before, we would want to try and factor both top and bottom and just see if anything does reduce right off the bat. So if I look at this first example, the top doesn't have the ability to factor, so fairly high likelihood that I won't get an exactly 2x minus 11 in the bottom. So for this one, I would want to multiply to the negative 8 and then add to the positive 2 in the middle. That should be a positive 2 and a negative 4, or sorry, positive 4 and a negative 2 that would satisfy that. So that would give me two factors, x plus 4 and x minus 2. So if I asked what is the domain, it would now be set those equal to each other. Notice our approach really is no different for vertical asymptotes, but instead of saying x cannot equal, with these I would actually say x can equal, because I'm actually creating an equation of a line. And all vertical lines, remember, have this formatting of x equaling something. In this case, it would be x equals negative 4, because that makes the first parenthesis equal 0, and then x equals positive 2 for the second one. And I do want to kind of stress that vertical asymptotes are equations of lines, so having this x in front is extremely necessary. In other words, if I asked you to just graph negative 4, that's not really enough info, whereas if I give you x equals negative 4, that would now give you the idea of, okay, that must be a vertical line. Whereas if I did not have that variable there, it's anyone's guess what that negative 4 might be. Maybe it's horizontal, maybe it's vertical, maybe it's just a dot. So again, just try and be as explicit as possible. Vertical asymptotes are equations of lines, so make sure that you include a variable. In this case, it's always going to be an x equals situation. If I look at the second one, now this time the numerator actually can factor. They both have an x in common, so I could factor that out. That would leave me with x minus 4. So if I get either of those factors in the denominator, then I should reduce first before I find my vertical asymptotes. If we look at the bottom, that x can be factored out of that as well, which then leaves x squared minus 1, which can factor even further to where the numerator again is still just the x times x minus 4. On the bottom, that's a difference of 2 squares, so that would be something I can use a conjugate pair for since the middle term is missing, of x plus 1 and x minus 1. So notice my domain would be x just can be anything other than 0, negative 1, and positive 1. But my vertical asymptotes will only come from the factors that are not in common. Well, the x that's on top and bottom technically would cancel out, so the only remaining factors, x plus 1 and x minus 1, are the ones I actually set equal to 0. So the first one, if I set equal to 0, I'd get x equals negative 1. Second one, if I set it equal to 0, I get x equals positive 1. And those would be my two vertical asymptotes. The factor that happened to cancel, that x that canceled on top and bottom, is actually going to be a different thing we'll talk about later in the video, which is what's called a hole in the graph. It still would be a number that gets skipped graphically because it's not allowed to be in the domain. It just doesn't happen to fall into this vertical asymptote idea because, again, it's only when there's factors that are not in common that I worry about setting equal to 0 on the denominator. All right, let's go ahead and move on to the third one here. I've got x minus 2 is as good as the top is going to get, but it does look like I can factor out an x in the bottom, which turns into an x squared minus a 5, which that's not a perfect square. So I could still set it equal to 0, but notice if I set x squared minus 5 equal to 0, I would add 5 to both sides. This one just happens to come back as a couple of irrational numbers, but that still is okay. So my vertical asymptotes for this problem are going to be, since none of the factors canceled out on top and bottom, one of them would just be plain x equals 0 from the x that was able to be factored out initially. The other two vertical asymptotes are going to come from the solving of the x squared minus 5, which gave us one positive square root of 5, and one negative square root of 5. So with this one, the domain, if this was a domain question, I still would have identified the same three numbers, and it just happened to be that all three of those numbers would have been vertical asymptotes, which is slightly different than what part B was. Part B, the domain still would have said x cannot equal 0, 1, or negative 1, but the 0, instead of it being a vertical asymptote, it would be something different, which again, like I mentioned before, is something we'll talk about a little bit later. But hopefully this makes sense in the fact that we're just looking for what the factors of the top and bottom are, reducing first, and then setting whatever is left on the bottom equal to 0, and then listing them out in this x equals format, again, because they are all vertical lines. After vertical asymptotes, the next best thing to try and identify when we're trying to analyze these graphs are things that are called horizontal asymptotes. Now, horizontal asymptotes, instead of being vertical dotted lines, these are actually going to be horizontal dotted lines. And it's basically another way of describing what's considered the end behavior, or the arrows on the left. So polynomials, normally we have arrows that either point up or point down, and that was something that we could base the degree, or use the degree, to kind of base our conclusion on. Horizontal asymptotes, on the other hand, are going to now flatten. So it could be from below, or it could be something where maybe it comes from above, but it's something that basically is just telling us our arrow, instead of pointing up or down, it actually is going to point sideways. And if we reference back, or maybe if you look at the PowerPoint that's in your notes, or in OneNote, and kind of take a glance at some of the examples from earlier, you'll notice that a lot of them did kind of flatten on the sides as opposed to actually spiking up or spiking down. So again, we could have something that basically describes what's going on the far left and far right, as again, that's what the horizontal asymptote is telling me, but it really is not saying anything about what's happening in the middle. So technically, if I wanted to, I could say a horizontal asymptote could be like that, where notice, yes, it did cross in the middle. That's not a big deal. Again, the horizontal asymptote is really just telling me what's happening on the far left, as well as what's happening on the far right. What happens in the middle is what all of the x-intercepts, or vertical asymptotes, or maybe just doing a t-chart, whatever happens in the middle is going to happen. So if they need to cross over horizontal asymptotes, that's fine. It's just, again, describing the far left and far right. Now, vertical asymptotes, because those are numbers that are actually getting completely left out of the domain, we never, ever, ever will cross over a vertical asymptote. So just kind of try and store that in your head. Of vertical asymptotes will never get crossed. Horizontal, or the next type, which are called oblique, those ones we can cross over if need be. And again, I'll kind of stress that a little bit more a little bit later. But anyway, as far as how do I identify or find a horizontal asymptote, we still are going to focus, as you can see with kind of some of the statements here, we're still going to focus on degrees, but I actually am going to compare. So we have basically three different situations that are going to happen, since I only have a single polynomial on top being divided by another single polynomial in the denominator. So what would happen is, since a polynomial only has a single degree, I'm really just going to compare two numbers. So there's three different things that can happen. Either they're going to have the exact same degree on top and bottom, and what you do at that point is you make an equation of y equals, because it's a horizontal, but it's going to be y equals, and then I just make a fraction with the leading coefficient. So essentially, whatever number's in front of that highest powered term, or wherever you got the degree from, I would just make that ratio of whatever number is on top over whatever number is on bottom in front of those highest powered terms. The next situation is the numerator could be smaller, or a smaller degree than what's in the denominator. In other words, the denominator has a higher power. At that point, you could say that the x-axis will be it, or just write it as a y equals 0, meaning it's going to get close to the x-axis, but on the far left and far right, it's just going to kind of flatten out. If it needs to cross it somewhere in the middle, so be it. Again, the horizontal asymptotes are just describing the far left and far right of my graph. The third scenario that could happen is the numerator actually has the greater degree. So in other words, the higher power is actually on top. At that point, you can actually make a conclusion of there is not a horizontal asymptote that I need to worry about. So again, three different scenarios. Either they're the same degree, which basically means I'll make a fraction with the coefficients, or there could be a bigger degree on the bottom, or the power on the bottom is larger than the power on top. Then at that point it's just y equals 0. And the third option is maybe the top power or top degree is larger, and then at that point we can just stop and go, there won't be a horizontal asymptote, don't need to worry about it. So let's go ahead and practice this with a little application of those rules. So let's go through each one of these. Part A, notice I have a degree in the numerator of 2, and I have a degree in the denominator of 2. These are the same. So what I'll focus my attention on are the numbers in front, and I'll just make a fraction with those. So the horizontal asymptote for this first one will just be y equaling 3/4. If that fraction could reduce, I would go ahead and do so, but 3/4 doesn't. So this would just have a horizontal line at about 3/4, so this would probably be more of an approximation when it came to graphing it, but again, that's just going to tell you what the far left and far right arrows will be doing for this particular function. If we move on to letter B, the degree on bottom is a 3, whereas the degree on top, even though it's not there, we could say that one's a 1. It's bigger on the bottom, so anytime the degree on bottom is larger, it will have a horizontal asymptote, and it will always be y equals 0. So notice I didn't have to do as much as I did with part A. I didn't have to worry about anything. It's just if it's bigger on the bottom, y equals 0 is the horizontal asymptote. And then the third one here, notice the degree on top, or the highest power on top is 3, so that's my degree. The highest power on the bottom is 2. Anytime it's larger on top, then at that point we can make a conclusion of there is no horizontal asymptote, so I don't have to worry about it. So hopefully that seemed relatively fast and simple. It's just a matter of comparing degrees and just making the correct conclusion from there. If it's the same, you make a fraction. If it's bigger on the bottom, it's 0. And if it's bigger on top, we don't have one. Now there are also a different type of asymptote, which is called an oblique, or sometimes books reference it as a slant asymptote. So again, the two keywords that you can use are oblique or slant. These ones essentially, instead of being perfectly horizontal or perfectly vertical, now these ones are more diagonal. So they're going to actually have more of a format, as you can see at the bottom here, of y equals mx plus b. They'll actually have a slope and potentially a y-intercept that I could find. Now when this happens, it will only happen if the degree on top is exactly 1 more than whatever the degree on bottom is. So thinking back to horizontal asymptotes, we just said if there's a higher power on top, it won't have a horizontal asymptote. So what we would do at that point is go ahead and move on to this idea and just go, well, was the power exactly 1 more on top? If so, I'll just end up doing long division to come up with whatever the quotient is, and it basically is, since I'm only going to worry about the quotient, it's going to mean that I don't have to worry about what the remainder is. So it's going to be essentially everything except for the remainder will turn into what my oblique asymptote equation is. And so the next couple of examples will kind of demonstrate why we talked about long division and whatnot. We technically could utilize synthetic division in certain scenarios, but for all of these I would highly recommend just make it a habit of just doing long division, and you're really only going to have to do 2 steps to be able to get an mx term and then a potential b term, and then once you have those 2 identified, you can kind of stop, because again, I do not need whatever the remainder actually is. So here's just a couple of examples of number 1. If we look at each one, the degree on top is exactly 1 more than the degree on bottom, so notice a degree of 2 over a degree of 1 for part A, or for part B, a degree of 3 over a degree of 2. So again, that's our identifier of yes, there will be an oblique asymptote, or again, you could call that a slant asymptote. Whichever phrase you prefer, go for it. But with this, what we would do is basically just set up our long division. Whatever is on top will go inside, and whatever is out, or whatever is on the bottom will go out front. And then we just go through our normal long division. I want the x to turn into x squared, so they would cancel, so I'd have to multiply by a single x, and then distribute it through on top, or with the front. So x times x would give me x squared, x times 3 would give me 3x. And remember, at this point we group and subtract, so x squared minus x squared does cancel as I was trying to. And then 4x take away 3x would give me 1x. And then I can drop the 1 down, not that it's going to be that important. At this point now I would just do, how do I make x match the x in front? Well, it would just be a plus 1. If you needed to write it just to verify for yourself that yes, it will in fact cancel, go for it. But ultimately at this point we've identified our slant asymptote by creating that mx plus b format. So the slant or oblique asymptote is going to equal the y equaling x plus 1. So again, it is necessary to have the y equals because if we are creating an equation of a line, it just happens to be this one has both x and y because I'm writing it in that slope-intercept format. If we go on to the second example, this one's going to be a little bit more complex than some of the long division that you've done so far, but it's not going to change a whole lot. Essentially, I would just write whatever is on top inside and whatever is on the bottom out front, and our goal still remains the same. So even though that had a power of 2 on it, I still am going to look at it and go, how do I make x squared match 5x cubed? Well, for sure I would need a 5. And then I'd also need one more x, so multiply by 5x, and then just distribute that through everything that's in front. So 5x times the x squared would give me 5x cubed. 5x times the negative x would give me a negative 5x squared. And a 5x times the 2 would give me a positive 10x. And notice I'm intentionally lining them up underneath their corresponding like terms, or in their corresponding column, if you want to think of it that way, such that now the subtraction step is going to be a little easier. So 5x cubed minus 5x cubed does cancel like I was trying to make happen. A negative x squared minus a negative 5x squared, well, that actually minus a negative would switch to addition, so it's really negative 1 plus 5. That would give me positive 4x squared. Then I have x take away 10x, that would go to negative 9x, and then the minus 1, as it has done in the past, would just drop down. So now I try and figure out how do I make x squared match this 4x squared. Well, that seems like I would just need to multiply by a positive 4. And at this point, if we're happy with yes when I write that first term down and I subtract, they would cancel. At that point, I've chosen the right thing. Since I'm not worried about the remainder, I can go ahead and stop that process and say that my oblique or slant asymptote for this one is going to have the format of y equaling the 5x plus 4. And so when it comes to what would I do with this info graphically, well, I would essentially just try and draw these lines as if I was normally going to do it, but instead of drawing it as a solid line, I would draw it out as a dashed line, and just recognize that this is going to describe how the arrows on the far left and the far right are going to behave. They're going to flatten close to these lines, and if they need to cross over them, they can. It's just a matter of, again, describing what the arrows are doing. So if we can kind of just make it a point to say for ourselves that the only asymptotes I can't cross are the vertical asymptotes, hopefully that'll make things safe for you. Everything else, these horizontal or oblique ones, if you need to cross it somewhere in the middle, it's a-okay. It's just, again, describing what the arrows on the far left and far right happen to be doing when it comes to sketching out my graph. So as I've mentioned multiple times throughout this video, the types of asymptotes you cannot cross are the vertical asymptote. So we're never, ever, ever going to cross vertical. If I need to cross over a horizontal or oblique, I guess I should also include or oblique. It's okay, but it doesn't actually have to cross over it. So it's basically just saying it's okay if you do, just kind of pay attention to what things are supposed to be happening. So if you have to cross over the x-axis because of an x-intercept, and you happen to have a horizontal asymptote that you would then have to cross in order to make that truly happen, it's okay. It's just the vertical asymptotes that I have to make sure that I don't ever, ever, ever cross over. So my hope is, by that sheer repetition of me saying never, ever, ever cross over a vertical asymptote, hopefully the more you hear it, the easier that will be to remember. If you have to cross the other ones, it's fine, just not on the vertical ones. Anywho, as mentioned earlier, we have a different way that we can skip over a number in our domain. In other words, if we had to get rid of a specific number due to setting the denominator equal to 0, it's not always going to be a vertical asymptote. As I mentioned before, sometimes it might actually be a hole in the graph. So again, just to provide that visual, let's say I could not equal 2 for whatever reason. Graphically, what that could be is just it's coming up maybe through that point and then right back out the other side. Notice that still is skipping 2 by having the open circle. So that is something I could do, but this would also potentially have like a vertical asymptote, it looks like, with how I just drew this example. So this would be one where I needed to get rid of maybe like 1/4, but then also needed to get rid of 2. Well, apparently the 2 would have been something that was actually one of those factors that cancels out. So again, how do I know when there's going to be a hole? It's when I factor and something happens to cancel out on top and bottom. Like one of the previous examples, I believe it had an x on top and an x on bottom that we're able to actually reduce, which then means there would be a hole at that x value. So in that case, it would have been 0. And then whatever the y value is when you plug it into the reduced version. So this part, it is important to note that you would always plug that into the reduced after you've canceled version to come up with the actual true y value. And then when it comes to plotting that point, instead of making it a closed dot like we normally would when we plot a point, we would just make it an open circle and then assume that the graph is going to come in one side of that point and then right back out the other. And that's where, again, all of the other analysis will kind of let me know how it's going to approach that point. Or when in doubt, you could also just make a t-chart, just see what some points near it happen to be, and then make it kind of go through those points nice and smooth. But again, with holes, it just goes in one side, out the other, and just make sure that you leave it as an obviously open circle at that point. So the next few examples will just be me working through or showing why something would have a hole. And I'll also talk about vertical asymptotes just so we can kind of see how they would interact with one another. So as we did earlier with these examples, we'll go ahead and start with, let's just see if we can get this into a factored form. Looks like x minus 2 on top can't really factor anymore, but on the bottom I should be able to multiply to a negative 2 and add to a negative 1. So if it helps, again, you could do a diamond factor, multiply to the constant, add to the middle coefficient, or the b value. In this case, what would satisfy those two statements? Well, a negative 2 and a positive 1. So I would be able to write this in x minus 2 and x plus 1 format. Notice at this point I would be able to reduce, so the x minus 2's would cancel, which at that point what that means is we have a little red flag of, okay, there's a hole when whatever makes that factor equal 0, which in this case when x equals 2, because again these two right here would be able to actually cross out or reduce. So that tells us, okay, whatever the 0 is of that factor is going to be where a hole is. So I can already say there's going to be a hole at 2 comma something. Well, what I want to do at this point is actually plug that number into our reduced version. So if I plug in, if that's our g now, if I do g of 2 with that, it would turn into 1 over 2 plus 1, which really would be 1/3. So the, I guess, coordinates, if you want to think of it that way, of the hole would be at 2 comma 1/3. So I would just do my best to get to that location, and I would just draw an open circle at that normal x comma y. Now as far as the remaining part, this 1 over the x plus 1, since there was a factor that didn't reduce, again, this is more of a review from earlier, I would just set that that factor equal to 0, and I would actually say there's a vertical asymptote at whatever makes that equal 0. So this one kind of has two things going on to get rid of a couple of numbers from our domain. One of them was a hole in the graph. The other one, it was a vertical dotted line that I would approach but not actually physically cross. If I move on to the second one, this one having a leading coefficient that's negative, my first instinct is to just take the negative out, so I now have something that's a little easier to factor. So this would then turn into a positive 2x squared, a positive x, but then switch the 15 to a negative. So again, notice I just took the negative out front right there. And then on the bottom, I don't really need to worry about doing that step. But here I would have to factor two different quadratics. So the first one I would have to do the ACB table. So if I wanted to maybe do some side work, I'll just do it right above it, I guess. 2 times negative 15 would be negative 30, so I'd want to do a factor tree, or diamond factor rather, with negative 30, and I want it to add to the positive 1 in the middle, which that seems like that should be a positive 6 and a negative 5. But again, there's this leading coefficient of 2, so I will need to actually simplify each of those by dividing by 2. So if I were to rewrite those as parentheses, the top is going to be, still has the negative out front that I took out at the beginning, but it would be an x plus 6, an x minus 5, but each of those over 2. And it looks like the second parenthesis is the one that won't be able to reduce, whereas the first one will. So I'm going to go ahead and just set this up where the next answer is going to be x plus 3 as one factor, and 2x minus 5 by bouncing that 2 in front of the x, just doing that little shortcut that we've done multiple times at this point. On the denominator, I would just need to multiply it to the constant. So for this one, it's going to be a diamond factor with what multiplies to negative 12 that will add to a negative 1. And in this scenario, that would be a, let's see, that would be a negative 4 and a positive 3. So my two factors in the denominator would be now x minus 4 and x plus 3. I guess I could have rewritten it in a different order, but whatever, I'll keep it the same. X minus 4, x plus 3. But now notice there is a common factor on top and bottom of x plus 3. So since those technically would reduce, and in the next line it would just be the 2x minus 5 on top and the x minus 4 on bottom, that tells us there's a hole because a factor canceled out at whatever makes that parenthesis that did cancel out equals 0. So x plus 3, what makes that equal 0? Well, negative 3. And then I would just plug negative 3 into this equation right here. So it would be what is f of 3 with the reduced version. If I plug 3 into that, I'd end up with 2 times 3 is 6 minus 5, so on top a 1. And then on the bottom, a 3 minus 4 would be a negative 1. So I could actually just rewrite that as a negative 3 comma negative 1, since 1 divided by negative 1 really is just negative 1. So that one was able to actually reduce a little bit. So there's how I would find the hole. And if I want to just review really quick, since there was still a factor in the denominator, it would just be set that equal to 0 now for my vertical asymptote. So if I needed to identify that, notice again I waited till after I reduced to then set the bottom equal to 0, and I found my two ways that this particular graph would need to skip over those two domain violations that I would need to get rid of x cannot equal negative 3 as well as positive 4 from looking right here. So again, hopefully this is all coming together and making it make sense as far as how do I actually approach these. I need to find a way to factor and reduce. If I happen to be able to reduce, the red flag that means is there must be a hole in my graph, so you may as well identify it as that step, I guess, happens. So everything from here on is basically just to kind of show how we bring all of this stuff together and actually create those graphs that we presented at the very beginning. So how we can come up with those kind of very oddly shaped graphs with a little bit of reasoning behind everything that we're going to do. So in your OneNote, you should be able to find a kind of a page of notes that really just breaks it down in a step-by-step process, just titled Steps to Graph Rational Functions. And ultimately, when it comes to any question that asks you to just graph a function and you notice it's rational, just go through each of those steps in order, and it should be able to allow you to collect all of the things that you need to be able to then put it all on a grid and do your best to kind of approximate or roughly sketch how things should actually behave. So each of these we'll work through in the next coming slides. So this may be a little bit time consuming from here on out, so if you feel like you understand the concept, you can stop watching the video. But if you feel like you need a few more examples or at least a visual of how all of this comes together, stay tuned, it's coming up next. So with our first example here, just kind of working through all of the steps, notice we have the first step is rewrite it in descending order if need be. This one already is written in descending order, so it's all good. So I can go ahead and move on to what is the domain of this problem. So the domain is going to be anything that makes the denominator equal 0 after I've factored it. Well, it's already as factored as it can be. So you can kind of do number 2 and number 3 as far as the steps kind of simultaneously. But if you were setting the bottom equal to 0, you for sure would have to factor it. It's just telling you may as well in step 3 factor the top at the same time. So for this one, it's just x cannot equal, in this case, -2 would make the denominator equal 0, so that's going to be my domain restriction. If I was able to factor and cancel anything out for step 3, then at that point I would move on to step 4 and identify any holes, but since there are no common factors on top and bottom, I can go ahead and with confidence say there are not going to be any holes on this particular graph. So then we can move on to our vertical asymptotes, which are essentially any remaining factors in the denominator, set it equal to 0 and solve. Well, that's just going to be x equals, and then whatever that number that makes the denominator equal 0, which happened to be -2. So I may as well go ahead and get that vertical asymptote drawn on my grid. So notice I'm just drawing a vertical dotted line that goes through -2 on the x-axis to represent that x equals -2 vertical asymptote. At this point we can move on to our horizontal asymptote. Well, I would look at my degrees for this. So degree on top is a 1, a degree on bottom is a 1. So I would essentially now just, because those are the same, say that yes, there will be a horizontal asymptote, and it will be equal to whatever the fraction of the coefficients happen to be. Well, the coefficients in front of those terms, since there aren't any numbers actually explicitly written, would both be 1, and 1 divided by 1 would remain 1. So I may as well get that also on my grid and just draw a horizontal line at +1. Since there is a horizontal asymptote, there is no way that I can have an oblique asymptote. So there won't be any oblique or slant asymptote, because the only way that it would have that is if the degree on top was larger, which then means I would not have had a horizontal asymptote. So it's always, if you identify a horizontal asymptote, you can with confidence say there's not going to be an oblique. If you say that there isn't a horizontal asymptote, then there potentially could be an oblique. So hence why we do it in that order. Start with horizontal and then follow it up with oblique if there happens to be one. But remember, oblique only happen when it's exactly one more when comparing the degrees on top. So I should be able to now transition, skip over the oblique asymptote, so step 6, the second half of that. I should be able to now go to my x-intercepts. So the x-intercept happens whenever the numerator, after I've factored and reduced, anything that could cancel out I would get rid of. So my x-intercept in this case is going to be whatever is left on top, set it equal to 0 and solve. Well, x minus 1, set that equal to 0, I get +1. So my only x-intercept for this graph would be at 1, 0. So just like we've been doing so far, may as well collect our points as we find them and put them on the grid. Next one I can do is the y-intercept. So with this one, my y-intercept is going to be just what happens when I plug 0 in, just like it has been for any other function. And if I plug 0 in for the x's, the numerator would give me a -1, and the denominator would give me 0 plus 2, so +2. So put it all together and I get -1/2. So I should be able to plot that point, which is seeming to make sense if we think in terms of how can I approach those asymptotes in a way that won't cross the vertical one. If I needed to cross over the horizontal one, I could have, but it seems to me like this part on the right side of the vertical asymptote is going to be something that's staying below that horizontal asymptote as far as logic is concerned. From here, it's just going to be, all right, well, I've got every point that was able to be found in a relatively easy way. Let's maybe just plug in some numbers that are relatively close to some of the things I don't know about. So some of the numbers I would think to try in this case are maybe -1 and -3, since those are close to my vertical asymptotes, or my single vertical asymptote, not plural. And then maybe something that's a little bit further to the left, so maybe something like -4 or -5. I don't know. Let's just do -4 and see if we can come up with a decent idea of what's going on. So if I plug those numbers in, -1 on top would give me -1 minus 1, so -2 over a -1 plus 2. It seems like that would just be a +1, and then a -2 over a +1 would just be able to be simplified to a -2. So I can go ahead and plot -1, -2. So I feel pretty confident right now that it's going to be spiking down close to this vertical asymptote, pass through those points, and then flatten off to the right, because that's really what a horizontal asymptote describes, is the arrow on the far right. So my only question mark really is what's happening on the left side of that vertical asymptote, and that's where the -3 and -4, when I plug them in, are going to be helpful. So if I plug in -3 on top, that would turn into a -4 over, and then -3 plus 2, that would be a -1. -4 over -1 would just be a, not -4, but +4. So I should be able to plot that point at -3 comma +4, so it seems like it's going to be up here. And if I did the same thing with -4 take away 1 would be -5 over, and then -4 plus 2 would be -2. And if I simplify that, that would turn into +5/2, which really is like 2.5. So if I go to -4 and up to 2.5, that would be right about there. Seems like to me, if I need to flatten over here on the left, it's probably going to be above that horizontal asymptote, and it seems like it's probably going to curve up through these points and point up here. Since again, I'm not supposed to cross over the vertical asymptote, that gives me a decent idea of what the shape of this graph would look like, and at this point, we're happy with it. We can always double check with maybe Desmos or a graphing calculator. But we've identified all of our key parts here on the left with what I did in yellow, made a little T-chart to give us a couple of extra, just kind of fill in the blank points. Could have maybe plugged in -5 or -6 just to see what happens if we felt still like we weren't confident with what was happening on the left. But once you get about 2 or 3 points, more times than not, you should be able to kind of see exactly how it's going to, I guess, go through the points, number one, but also how it's going to approach those asymptotes that we identified. And again, the horizontal asymptotes just tell us what the far left and far right arrows are doing, whereas the vertical asymptote is something I can't cross, so I know it either has to go up or down depending on what the other points around it happen to be doing. Alright, got 3 more examples to work through for you. So again, all of these are just giving you opportunities to be able to see exactly how to approach these. So if you don't feel like you need to watch these anymore, feel free to, I guess, stop watching the video and just start working on the practice. But I've got 3 more to go, so if you want to hang in there, good on you. So with this, again, we would start with making sure it's in descending order on top and bottom. If I could factor, I may as well factor at this point, but ultimately the top doesn't factor because nothing would multiply to -1 that will add to 4, so the top really is as good as it's going to get for the time being. So my domain is the next thing to identify, which is just anything that makes the bottom equal 0, which is -3. I just need to get rid of that number, so my domain is x cannot equal -3. Moving on, I would go ahead and just maybe try and identify if I could factor, and if I do have anything that cancels on top and bottom, identify any holes. But since the top can't be factored, I know at this point there are no holes. So that's good. I don't have to do that extra work. At this point, I would go ahead and figure out my vertical asymptote. Well, the vertical asymptote, since there still is a factor on the bottom, x plus 3, it would just be whatever makes that 0, which we already identified earlier as -3. So this one has a vertical asymptote at that -3 number. So just like before, go ahead and put it on the grid as you find them. Moving on to the next thing, horizontal asymptote. Well, the degree on top is a 2, the degree on bottom is a 1. Since it's bigger on top, that's the situation that had no horizontal asymptote, but it does have an oblique asymptote because it's exactly 1 more on top. So we'll go ahead and do, let's see, where do I have room to be able to do this? I'll do it up here. Do the long division with those values, so x squared plus 4x minus 1. Again, remember, all I really need are the first 2 terms of this quotient. So what do I need to multiply by to make x match x squared? That would just be a single x. And go ahead and multiply it, and then subtract. Well, 4x take away 3x would just be 1x. And if I go ahead and think in terms of how do I make x match x, I'm pretty confident it's going to just be 1. And yes, they would subtract in the next one. Since I don't need the denominator, I can go ahead and stop and say, well, my oblique asymptote is the quotient I just found, which was x plus 1. So that would be a y-intercept at 1 with a slope of 1. So if I go ahead and just plot as many of those points that have that slope of 1 from that y-intercept, that at least gives me a bunch of things that maybe I could try to connect with a dotted line. So this is basically going to tell me that one of my arrow on the far right is going to kind of point up, whether it's above or below. Kind of depends on what happens with the other points, but I know one arrow is going to point up to the right, the other arrow is going to point down to the left. Now what happens in between? If it needs to cross over it, we'll let it. It just is a matter of I cannot cross the vertical asymptote, as mentioned multiple times in this video. So now it would come down to, since I had the oblique asymptote, finding my x-intercept. So my x-intercept for this one is going to be anything that makes the numerator equal 0. So it looks like to me I'm going to have to solve a quadratic. So I could try completing the square. I'm going to go ahead and do it that way. So x squared plus 4x equals 0. I would add the 1 over to make it positive 1. And then come up with a number that's missing. So in this case, half of 4 would be 2. Squared is 4, so I would add 4 to both sides. And then that should allow me to rewrite this as the factored version x plus 2 quantity squared, because that's what multiplies to 4 and adds to 4 is a pair of 2's. And 1 plus 4 would give me 5 on the right side, so it looks like I'd take a square root and then subtract a 2. So my x-intercepts for this one are going to be at -2 plus or minus whatever square root of 5 happens to be. So I'm going to go ahead and figure out the decimal values of each of these, since that's going to be more helpful than the exact version when it comes to actually typing into or plotting the points. So it looks like I've got one x-intercept. If I use the -2 plus rad 5, it would be at about 0.24-ish. And then the second one is going to be -2 minus the square root of 5, which is approximately -4.24-ish. And again, each of the y values for that would be 0, so I'm going to go ahead and plot those on my grid. So positive 0.25-ish would be right about there, and -4.25-ish would be right about there. My y-intercept in this case would be whatever happens when I plug 0 in, so that should just be the -1 left on top, and a positive 3, 0 plus 3 on the bottom, positive 3, so -1/3. So this is going to be another approximation. And just based on where that x-intercept was, that seems kind of reasonable if I think in terms of how I'm going to approach my vertical asymptote as well as finish close to the oblique asymptote. So as far as from here, it's just going to be fill in the blank with some numbers to try. So I feel like maybe -6 on the far left might be a good one to try. Maybe -2 just to the right of that vertical asymptote. -4 might not be terrible, but I've already got a point really close to -4. Maybe even +2 just to see really what's happening over on that side as well. So if I were to plug each of those in, -6 squared would be a 36. Plus 4 times -6, so it would be -24, then -1. So the numerator would be for that one 11 over -6 plus 3 would be a -3. And 11 divided by a -3 is approximately -3.7-ish. So if I were to go to -6, I'm going to go down to about -3.7-ish. So right about there. I feel like actually the left side, I got a pretty good idea of it's going to come through these points like this and kind of spike up to the right, just utilizing those two. And I kind of feel like I should know what's going to happen on the right, but let's just try -2 just to really make sure. So -2 squared would be 4 plus 4 times -2, so -8, then -1 would give me a -5 over, and then -2 plus 3, that would be +1. So -5 is the x-coordinate, or the y-coordinate of that one. So -2, -5, that's a nice point to be able to plot. I feel like that one has given me enough info that it does go through these points this way, and then it's just slowly going to approach that oblique asymptote once again. So notice I ended up actually putting 4 different arrows on here. Again, that's mainly due to this vertical asymptote caused a break in the graph. It does continue up forever as well as down forever on the, I guess up forever on the left, but down forever on the right. but I actually never would touch that number. So it just spikes really, really fast, but does still technically keep getting closer and closer to that -3 that we were able to leave out of the domain. All right, last two examples now. Seems to me this is one that I could probably factor right off the bat. It already is in descending order, so step 1 is already taken care of. Step 2, I'll need to set the bottom equal to 0, so I'll need to factor anyway, so why not just try and figure out all of the factors of the top and bottom since we're doing it. So the top I need to multiply to -4 but add to 0, so that should be opposite numbers, +2 and -2, otherwise known as the difference of two squares that turns into a conjugate pair. On the bottom I want to multiply to a -6 but add to a -1, so that seems like that should be a -3 and a +2. So notice with this one, I do end up getting something cancel, but I still want to identify the domain before I do any canceling. So the domain for this one is going to be x just cannot equal whatever makes the bottom 0, so it looks like +3 from the first parenthesis and -2 from the second parenthesis. Since there is a factor that cancels, this x plus 2 will be able to reduce, so I actually can rewrite this as x minus 2 over x minus 3. But because something canceled, I know that there is a hole, and it's going to be at whatever the x coordinate is that makes that parenthesis equal 0. So if I set x plus 2 equal to 0, I'd get -2. And now I just need to figure out what the y coordinate is, which is going to be plugged into the reduced version. So that looks like -2 minus 2 on top would be a -4 over a -2 minus 3, which would be a -5. So I could reduce that and just really say that that's a +4/5 instead of having the double negative. So I'm going to go ahead and erase that and just write that where I cancel those two negatives and make it a positive. So as far as things that I've identified so far, I've got a hole at -2 and whatever 4/5 would be, so just a little bit less than 1. So I'm going to go ahead and just put an exaggerated open circle at that location. Now the vertical asymptotes are going to be anything that makes the denominator equal 0 from here. Well, the x minus 3 is all that's left, so that means x equals 3 is going to be a vertical asymptote. So over here at +3, I'm just going to throw my vertical dotted line on my grid and just know I'm not going to cross over that number. So I'm either going to spike up or spike down as I get close to that. Now we can move on to our horizontal or oblique asymptotes. In this case, I have a horizontal asymptote because the degrees on top and bottom are the same. They both were 2 originally, or with the reduced version, they're both 1s. Doesn't matter which one you look at, it's still going to give us the same value. The coefficients, since they are the same, is what I would need to make a fraction with, and on top it's a 1, on bottom it's a 1, and 1 divided by 1 would still be 1. So notice that gives me a horizontal asymptote pretty close to that hole. The hole still was just a little bit below it, but at least it gives me an idea of what is going to happen on the far left and far right. If I needed to cross over it, like I said earlier, so be it, but we'll figure out what the other points end up turning into. Now, since there was a horizontal asymptote, that means there cannot be an oblique asymptote, so I'll go ahead and just write there is not one, and move on to the next thing, which is the x-intercepts and y-intercepts, which really there's only going to be one single y-intercept. There could potentially be multiple x-intercepts, but with this one, it's just going to be with our reduced version, the x minus 2. If I set that equal to 0 on top, that gives me just one single answer, +2. So I'll go ahead and say +2, 0 is my x-intercept, so may as well plot that, +2, 0. Got it. And on to now the y-intercept, which would be plug 0 in. Well, that should just leave -2 on top and -3 on the bottom, and two negatives would turn into a positive, so +2/3. So it seems to me that I've got a pretty good idea of what's happening on the left. It's going to flatten, go to that hole, come back out the other side, but then kind of go through those points, and it looks like it's probably going to have to spike down. Just based on each of those points, we're technically getting lower and lower, so that seems reasonable. So now it's to the last step, which is let's fill in the blank with what we don't know yet. Well, it seems like the only thing we don't know is what's happening to the right of the vertical asymptote, so maybe trying numbers like maybe 4 or 6 or even 5 or 7. It doesn't really matter, just a couple of points to give us an idea of what's going to happen. If I were to plug those into the reduced version, again, 4 take away 2 would be 2 over 4 take away 3, which is 1. So that's going to be at 4 comma 2. 4 comma 2 right there. And if I were to plug in 6, let's see what happens. 6 take away 2 would be 4 on top. 6 take away 3 on the bottom would be 3. And 4 over 3 is about 1.3. So if I go over to 6 and go up to 1.3, that would be right about there. So it seems to me like this must be, since that came down, must go down from that vertical asymptote through those points and then flatten off to the right near the horizontal asymptote. So again, notice we're just collecting all of the info, putting it on the grid as we go, and then just thinking logically through how could I potentially connect these points without breaking any rules like crossing over a vertical asymptote. Hopefully the examples I've done so far have at least made that make sense, but if you still felt like that wasn't enough points, just keep adding some more to your T-chart right here. The more points you have, the more accurate it will be, but usually with at least a couple of points on each side of the vertical asymptote, you can kind of get an idea of what the shape actually will look like. Alright, now on to our fourth and final example. If you're still watching, thanks for hanging in there. So for this one, again, we would start with, is this in descending order? It sure is. So I don't have to worry about step 1. May as well go ahead and jump to step 2, which is identify the domain. So on the bottom, what multiplies to -1 that adds to 0, that would be a +1 and a -1. But while I'm at it, I may as well factor the top as well. So this would be an ACB situation. So 3 times -2, that would give me -6. So I want to multiply to -6, but add to a -1. It seems like a -3 and a +2 would accomplish that feat. But I do have this 3 in front, so I'll have to divide by that. So I'd end up with an x minus 3 over 3, which would turn into an x minus 1. And then the other one's going to be an x minus 2 over 3, so that's the one that the 3 would move out front. And actually it would have been x plus a 2 over a 3. So 3x plus 2 is what that one would turn into. So notice I did get a common factor, x minus 1, so this one will have a hole. But before I get there, let's identify what numbers need to get skipped. So the two numbers that need to get skipped according to the denominator are a +1 and a -1. So I'd make sure that I identify those. There is something that will reduce, so I know there's going to be a hole at whatever the 0 is of that factor. So since it's x minus 1 that's going to get to cancel, that means +1 is going to have a hole. I just need to figure out what is the y coordinate. And that's going to come from plugging into the reduced version after I've canceled that factor. So now if I plug in 1, I get 3 plus 2 on top, which is 5, over 1 plus 1 on the bottom, which is 2. So at about 1 comma 2.5, I'm going to end up having a hole on this graph. So I'm going to go ahead and just throw that one on there. At this point, we can move on to vertical asymptotes. So any factors that still are remaining on the bottom, anything that makes that equal 0 is going to be a vertical asymptote. So in this case, that would be x equaling -1. So just like we've been doing this whole time, go ahead and put a vertical dotted line there telling us we're not going to cross over that number. Move on to horizontal asymptote. Let's see, the degree on top is 1, the degree on bottom is 1. So this one's going to be a make a fraction with the coefficients. So on top the coefficient is a 3, on bottom it's a 1. So 3 over 1 would just be 3. So I've got a horizontal asymptote this time at y equals 3. So once again, just throw it on the grid as you find it. Since there was a horizontal asymptote, there's no oblique, because the power on top would have had to be 1 more, just to remind you why. So since they were the same, there's no way it had an oblique. And now move on to our intercepts. X-intercept is going to be whatever makes the numerator equal 0 from our reduced version. Well, if I set 3x plus 2 equal to 0, I would subtract 2, then divide by 3, so -2/3 would be the x-intercept. The y-intercept is going to come from plugging 0 in. Well, if I replace the top x with 0, it leaves 2. If I replace the bottom x with 0, it leaves a 1. And 2 over 1 would just be 2. So the 2 points I've got would be at negative 2/3, comma 0 on the x-axis, and at 0, comma 2 on the y-axis. Seems to me like I feel pretty confident what's happening on the right side. It's close to the vertical asymptote, passes through these points, gets to the hole, goes in one side, back out the other, and then flattens close to the horizontal asymptote. As far as the right side is concerned, it looks like I should be able to plug some numbers in. Maybe plug in negative 2, and maybe negative 3 or negative 4. I'll just go with negative 3 just to see what happens. If I need to plug in negative 4, I will next. But if I plug in negative 2 times 3 would be negative 6, plus 2 is negative 4 on top. Negative 2 plus 1 on the bottom, that would be a negative 1, so that's just going to be at positive 4. So negative 2, comma positive 4 right there. And let's see what happens when I plug in negative 3. What happens? Negative 3 times 3 would be negative 9, plus 2 is negative 7, over a negative 3 plus 1, which is negative 2. So that's going to be half of 7, which is 3.5-ish. So plot that point, negative 3, comma 3.5 right there. That was a little bit below, so it seems like it's approaching our horizontal asymptote from above, and then spiking up through those points, making sure I don't cross over the vertical asymptote. And voila, we've got enough points to be able to at least be reasonable or reasonably close to the true graph. But again, the more points you put in that T-chart part, if you wanted to plug in more, go for it. But all the ones, if I kept going further left, would just get closer and closer to that positive 3 value. They'd just be a whole bunch of decimals. So I'm guessing if we even did one more, you probably still would have been able to make the conclusion of how it was going through those points. Anywho, hopefully these last 4 examples have kind of helped with the idea of how do I approach these problems, how do I make these graphs happen. But if you do have questions, just reach out to either myself or Miss Bass, and we'll do whatever we can to try and work through more examples until it finally starts to click. Appreciate you taking the time watching the video. For those that did stick it out, I guess I will catch you next time.